Hello everyone, thank you very much by this opportunity to present my current research. My name is Lucio Agostinho Rocha, and I will do this presentation. My current affiliation is the Federal University of Technology Campus Apucarana, Brazil. The title of this research is, An Architecture for Predictive Path Planning on Simulated Robotics. This presentation is been presented in the 9th International Conference on Computer-Human Interaction Research and Applications. In this slide, it is done a short resume of this presentation. The lecture outline will cover predictive path planning concepts, research objectives, the proposed methodology, the formulation for path planning, the evaluation and results obtained until now, and finally, the final remarks. In this research, the problem that is addressed is an evaluation of machine learning algorithms. Machine learning algorithms can be used for predictive path planning on simulated robotics. So, path planning is an informal technique to obtain trajectories to reach destinations, and there are many important applications related at this research. For example, navigation in geographical maps, routes in vehicular networks, job scheduling problems, and many others. In this research, machine learning algorithms are used to do predictions, and these predictions contributes to obtain better trajectories with near-optimal solutions. Then, the evaluation is been done with simulated robotics. The results indicate that this proposed methodology is a good alternative to give feasible paths for robotic navigation. One of the main motivations of this research is to apply machine learning in mobile robotics. In mobile robotics, path planning is an alternative to reduce the computational cost to reach targets. As a consequence, path planning gives opportunities to discover many alternative paths. Also, if there static are obstacles, such as walls, or dynamic obstacles in the environment, a good planning contributes to deliver with better quality. In this sense, there are many applications that can use path planning, for example, task distribution, mapping discovery, fault tolerance, decentralized networks, logistics, and so on. An important thing about these applications, the solution can change with dynamic obstacles in the environment. Due to this research also contributes for multi-agent reinforcement learning, when robots learn new paths, by doing new things. This research proposes an architecture to really implement predictive path planning. However, when the number of paths is very high, the computational cost is elevated. As an important consideration, this research proposes an architecture that gives paths, and this discovery is done when the robot moves in the environment. The many paths are modeled as transportation problems of the operating research area. So, the contributions of this research are: an evaluation of machine learning to optimize the path planning. The modeling is done with multi-layered flat networks. Also, linear programming is done with machine learning, and both works together to found feasible solutions. Also, the implementation of this architecture reduces the computational time to found solutions. And finally, the discovered paths are feasible for mobile robots. Now, look with attention this simple animation. The robot needs to know the path to continue its movement. Then, it is necessary a fast solution to reach a target. In this animation, source nodes are the circles, and the destinations are the rectangles. Each layer has many sources, and many destination nodes. A robot will choose the path with minimum cost, because the robot needs to save energy. The computational cost to discover the paths is high when we have many alternatives. In this methodology, a large set of paths is modeled as a transportation problem. In this transportation problem, the link capacities are randomly distributed on each layer. Each layer has the same amount of sources and destinations, to always give feasible solutions. On each layer, restrictions of demands are defined between the sources and destination nodes. The solver mission is to found a combination of links, that minimizes the restrictions of each layer. The restrictions of demands are randomly distributed on each layer. When the solver of linear programming runs, the solution gives the paths with minimum costs. This solution is transposed in an array. Finally, the robot uses these solutions in the array, and choose the best movement for navigation. In order to illustrate an example, this slide shows some parts of the modeling for the node 1. This transportation problem is automatically generated, and a large set of variables is easily found. In the upper side of this slide, the fragment illustrate how the links are modeled in the objective function. Then, in the bottom side, the fragment illustrate the source restrictions for a single node, and also the destination restrictions for a single node. It is important to note that, for a single node, the number of variables is high, and the solver has difficult to solve this model in reduced time. In order to perform a navigation, the robot use solutions from a dataset. This dataset is generated by this proposed architecture. In this architecture, the hard generator creates a flat transportation problem. Then, the hard solver runs, and solve this model. In the next, the hard formatter translate the solution found to the array. This procedure runs many times, until the dataset be filled with many arrays. Each array in the dataset is a feasible solution, with different link restrictions. The hard trainer runs a pre-train for the machine learning algorithms. A tuning is previously done with the hard tuning component. The next phase is computational faster, because the dataset is ready to receive requests. It is important to note, the hard phase already done the training. So, the prediction already have training data to do new predictions in faster way. Then, the soft prediction component can request on-demand solutions for new paths. The soft prediction component gives a prediction. This prediction can found any field in the array. This prediction is near optimum, and very closer at the best solution found in the previous hard phase. A path is obtained choosing the links with minimum cost. The motivation is to reduce the energy consumption by choosing low-cost links. So, the LP solver computes a transportation problem in the hard phase. For each solution, the link capacities, and the fitness found, are put in the array. This transportation problem is modeled as follow, n layers, and each layers has p sources, and the same number of p destination nodes. The objective function minimizes the summation of link capacities, in the layer A, between the source link B, and the destination link C. In order to produce as always feasible solutions, the link capacities must be non-negative. Also, the total of resources provided by source nodes must be equal the total demand. Note that variations can occur inside the layer, but resources provided and the resources consumed must be the same. Finally, the feasibility property guarantee always feasible solutions on each layer. In this slide, is presented the machine learning formulation. In the soft phase, machine learning algorithms try to predict the same fitness in lesser times. Again, the dataset is already found. This dataset is composed by many feasible solutions, with different link capacities and restrictions. In the soft phase, the machine learning uses a supervised learning. Each array has the link capacities and the fitness. A regression step is done, the training set, and the test set are used for predictions. So, the optimal solution is the target of the prediction. In this formulation, 11 is the ITH feature for the fitness prediction from the ITH array. Then, it is done a multiple linear regression, because this feature is composed by the array. The chosen 11 array has all link capacities and the fitness, for a specific combination of link capacities and restrictions. In this formulation, Y value gives the prediction fitness for a new combination of link capacities and restrictions. This result is faster than compute with linear programming. So, in the next, the results obtained with this strategy are evaluated. The running environment was done in a notebook, with Ubuntu Linux, GLPK solver, and scikit-learning libraries. In this table, the chosen machine learning algorithms are shown. These algorithms have good performance to realize predictions in short time. The sampling, to compose the dataset, is done with different number of variables. 100 samples with 2000 variables in each LP model. 100 samples with 8,000 variables in each LP model, and 100 samples with 18,000 variables in each LP model. The machine learning proportion for training and test is in the 4/1 proportion. This means that, in 10 samples, 8 arrays are used for training, and 2 for tests. In this slide, the average time to do predictions is shown. Note that, the major of machine learning algorithms can perform well when the dataset is previously trained. For the most of the chosen algorithms, The time prediction is below at tens. This give a good starting point to continue the next evaluations. In this slide, the error of the predictions is shown. The error indicates the difference between the expected fitness and the fitness found with predictions. Note that major of machine learning can obtain predictions with low error. However, for all of them, increasing the number of variables also increases the error. So, the chosen for an algorithm with low error is essential. In this slide, the precision metric is shown. This metric indicates how often true positive predictions are found. True positive predictions are given by results with low average error. So, this result indicates that the major of machine learning algorithms were node precise, even with a large set of feasible solutions in the dataset. However, gradient boost regressor, and also random forest regressor obtain the best results. In this slide, the results are very similar at the previous one. In this slide, the metric of accuracy classifies the better true solutions, according to true positives and true negatives found in the samples. Again, the results indicate that the major of machine learning algorithms were not accurate, even with a large set of feasible solutions to do predictions. Again, gradient boost regressor, and also random forest regressor obtain the best results. Now, look at this simple simulation. This simulation demonstrates an implementation of this architecture. In this simulation, the robot requests a new orientation when it finds a green area. In each green area, the machine learning computes the movement according to all possible paths. Then, the machine learning algorithm gives a new orientation for the robot according to your position. The new orientation is the minimum cost to reach the next destination. In this article, it is proposed an architecture to do path planning for simulated robots. As observed, solve faster is not synonymous of quality. Increasing the number of paths also increases the error, and this can compromise the accuracy results. In this case, the dynamic tuning of parameters can use these metrics to perform better predictions. Also, mobile robots can improve its navigability with machine learning predictions and suboptimal solutions. Also, the strategy of pre-train the dataset can increases the running time and contribute to obtain better solutions. Finally, as future works, it has been done efforts to compare machine learning algorithms and also simulation of trajectories in geographical maps. Okay, I will appreciate your help to continue this research. Do not hesitate in contact me. This is my email. Thank you very much.